Welcome to Massive Open Online course on Chemical Process Intensification. So, in this lecture we will discuss something about mechanism of intensification, that is happened by mixing, and in the previous lecture we have discussed the mechanism of intensification by some other means. So, in this lecture we will get into that mechanism of that intensification by mixing. And you know that first of all you have to know that mixing principles, what is that mixing. So, it will be a term of that implies homogenization or reduction in the variability of concentration, temperature, etc. That means in a suppose system where we have actually discussed in the previous lecture regarding the mechanism of intensification by multiphase mixer, and in that case to get into intensive mixing of those phases, you have to know the mechanism of mixing phenomena. Now, that mixing will happen based on what means that you are mixing the system in such a way that the concentration of the phases throughout the reactor or throughout the process system should be uniform. So, that is why homogenization term is coming. So, mixing should be a term where that homogenization of the system will be applied. And another important feature of that mixing is that you have to reduce the variability of the concentration. That means throughout the reactor you have to get the concentration of the phases in you know that uniform. So, if your intensity of the mixing will be a certain degree, so that your concentration will be distributed throughout the system uniformly. And also not only that concentration distribution, there should be a temperature also, that you have to mix the system in such a way that suppose in a heat transfer equipment or some other reactive system where temperature is also one governing factor. So, in that case you have to distribute the heat throughout this mixture in such a way that the distribution of the heat should be uniform. So, that is why mixing is a term that implies that homogenization of this concentration, temperature, or is there any other, suppose hydrodynamic characteristics are there, how it can be actually homogenized into the system. Suppose there is a gas liquid mixer where that you know there some certain chemical process is going on based on this gas liquid mixer, where droplet or bubbles are forming there. So, you have to distribute that bubbles or gases inside the liquid in such way that the in all location of this system that bubble concentration should be uniform or droplet concentration should be uniform. So, you have to mix the system in such a way, you have to use the gas distributor in such a way that all the locations in the or cross sectional average variation of this concentration of this bubble number should be uniform. Also, it is important to know that the scale at which this variability exists and the various mixing mechanism which reduce it. So, in that case you have to scale the process in such way that this variability where that like concentration, temperature or other, if is there any variables is there, so that mixing mechanism should be implied in such way that or designed in such way that reduction of this invariability or heterogeneity in the column. And most mixing process occur alongside heat and or mass transfer operations and chemical reactions. So, where mass transfer in heat transfer, reactive mass transfer, even other chemical engineering processes of multi-phase systems, their mixing characteristics very important. So, for mass transfer operation you have to mix the system in such way that if you are getting that well mixed concentration or well mixed temperature distribution there, you can get the better mass transfer. And also chemical reactions where suppose slow reactions, in that case you have to mix the gas liquid system in such way that interfacial area should be well managed, well distributed, through which that mass transfer will be carried out. Whereas in the fast reactions you will see there may not be the distribution of the bubbles or droplet. In that case you can use some other designated unit where that low residence time will be enough to get the better mass transfer operation. In that case you have to develop the device in such way that gas liquid contact time will be less, and they are that like channel based or microreactor system where fast reaction can be done based on this intensive contact and getting plug flow phenomena. That means they are only the interfacial phenomena where get the less residence time, but the fast reaction will be there. So that is why you can say that mixing is one of the important hydrodynamic phenomena in any chemical engineering processes where multi-phase flow systems are taking part for that particular process. Now if I say that in any reactor that your chemical engineering process are being carried out, in that case you have to use some reactor where that reactions will be carried out. So in that case reactor engineering starts with a simple mass balance where your reactions will be carried out. So in that case suppose there is a reaction, so what should be the inlet in the reaction reactor, and if is there any generation or consumptions of the reactants whatever actually allowed to pass into a reactor. So in that case inlet and the generation plus consumption whatever amount will be there, that should be balanced by the outlet concentration or outlet stream, amount of outlet stream and the accumulation if is there in the process. So in means here inlet stream, amount of inlet, and generation plus consumption is there any products is generated or suppose any reactants are consumed. So in that case you have to take into account those terms, and also that whatever stream is out is coming out, that you have to measure what the amount of stream is out coming, and also the if is there any accumulation is there. Accumulation is possible where the inlet and outlet streams are not in a same measure. That means here if inlet is greater than the outlet, then you can say there should be some accumulation. If suppose outlet is greater than the inlet, then you can get the negative accumulation. So in this way you have to balance that reactive system in a reactor engineering by mass balance, and the rate of this reaction in a well mixed system is governed by the reaction kinetics. So in this case the mixing phenomena is the important characteristics where that rate of reactions will be depending on this degree of mixing. So rate of the reaction is in the well mixed system is governed by the reaction kinetics, which depend only upon the concentration of the species and the temperature. So you have to distribute that temperature and that concentration of these reactants in the reactor in well manner. However, not all systems are well mixed, you can say particularly at larger systems, and mixing can be they are a rate determining for process intensifications. If suppose your system is wider in size, so in that case you will see there will be a gas liquid mixing or gas liquid solid mixing will be there, but there will be a generation of circulation cell inside the reactor. So if you are mixing those systems in the reactor, you have to develop the system in such way that there should be less back mixing generally for reactive system, whereas for heat transfer systems back mixing sometimes it is advisable, whereas in reactive system it should not be there. And so the mixing is a rate determining steps or rate determining factors for the process intensification there. And sometimes this wider size reactor may sometimes give the less performance due to this back mixing of the fluid. So there you have to use some mechanical provision so that you can reduce that back mixing. Sometimes three-dimensional columns in such way that your width and breadth should be less compared to the length, and sometimes you have to design in such a way that they are that only there will be a width will be very less whereas length will be high. So that will be called pseudo two-dimensional systems or two-dimensional unit where that you can reduce one directional mixing there. Sometimes that if there suppose three-dimensional mixing is there, so at least in 2 dimensions you can reduce that your mixing, back mixing. So you have to design that system in such a way that how it can be actually optimize that mixing phenomena. And also you will see that if suppose in their fluidization operation gas solid reactions are there where that adsorption is going on the solid surface. So if you are having the system in such way or design the system in such way that there will be back mixing of the solid particles, there may be a that less performance of the mass transfer from the gaseous stream to the solid stream, because the whatever adsorbent you are using as a solid particles, that should be get back to the original position or circulated, so that due to that pressure differences there may be a that desorption as well as adsorption should be simultaneously happen. So there may be that hindering of that the performance of the mass transfer. Other important task for the designer is that the prediction of the degree of mixing and the residence time of the species in the vessel. So is a certain reaction that sometimes depends on the residence time of the reactants. So you have to design the system in such way that for a certain degree of mixing what should be the residence time of the reactants that you have to predict or you have to estimate. So by generating some models that you can predict that degree of mixing and the residence time, and there are several methods to find out or estimate the degree of mixing like that tracer technique methods, even some other techniques also they are available to find out that degree of mixing. The tracer technique mixing is one of the important technique by which you can predict the degree of mixing. Like that you have to insert some tracer in a reactor, along with that that liquid stream or fluid stream you can say, and then you have to collect the sample from the certain distance of that reactor or at a certain position, and after collecting that sample with respect to time you can get a certain profile of that concentration variations with respect to time. And after that if you get this profile and compare with a certain model, like there is a important model, it is called tank in series model or axial dispersion model. If you feed those concentration versus time data with that axial dispersion model, then you can get some parameters which will be actually expressed as that Peclet number. So that by which you can calculate what should be the degree of mixing. The degree of mixing depends on that dispersion number or Peclet number. Dispersion number actually defined as 1 by Peclet number. Peclet number is actually basically is a that as a function of fluid velocity and the effective length of the fluid mixer which is lying in the reactor. So to find out that degree of mixing, that you have to estimate the dispersion number, that means Peclet number you have to estimate, then 1 by Peclet number, that will give you the dispersion number. If dispersion number is infinity, that you can say that your reactor fluid mixing will be well mixed and homogenized. Whereas if dispersion number is going to 0, that means there will be a 0 mixing, or it will be that no mixing you can say. And for infinity case, dispersion number if it is infinity, then you can say the complete mixing or complete homogenization. And based on that you can get that that residence time of the distribution of the species in the vessel. So the designer actually find out this degree of mixing as well as resistance of the species for analysis of the reaction for that particular process. And also another important task for the designer is that what should be the rate of species which are created or destroyed in a reactor that requires for that particular reacting system to actually give the yield of the process. So, that depends on the mixing characteristics, and also it will you know that effect on the reaction kinetics. That means what should be the reaction is going on, that some activation energy or temperature effect that will give you that kinetics of the reactions, like reaction rate constant, or you can say that the activation energy of the systems, how it will be there in the reaction system. So, that can be actually calculated based on this degree of mixing. So, if you are having that more mixing, then you will get automatically the different value of that activation energy and the constant rate of reaction. So, these are the important criteria for the designer to develop a systems based on these mixing characteristics for the process intensification. And a designer nowadays they are actually procuring different devices based on this mixing characteristics, and they are trying to reduce the size of the reactor. So, in that case reduction in scale is one of the important aspects for the process intensification. Now, what happen when the scale is reduced for that process intensification? So, the reduction in scale implied by intensification has many desirable consequences for chemical engineering operations, like the lower mass and heat transfer resistance enabled by the reduction path lengths of the diffusion or conduction interfaces. So, if you are making a system in such way that suppose micro channel based reactor. So, in that case you will see that path lengths may be very small for the diffusion or the conduction through the interfaces. So, in that case you can get the lower mass and heat transfer resistances, so that your performance of the mass transfer operation and heat transfer operation will be enhanced. And also important factor is that coupling with the more intense fluid dynamics in active enhancement equipment, where you can say that based on this mixing phenomena you can intensify the equipment. You have to develop the equipment in such a way that if you use suppose some baffles or some provisions, mechanical provisions inside the reactor to get reduced the back mixing of the system, then you can of course intensify the process of your chemical engineering operations. So, to get the intensification process you can use sometimes some shear producing mechanical device are being used in the reactor or in a certain chemical engineering process equipment, where you will see sometimes static mixers are being used, sometimes some bubbles, some that impeller systems are being used in such a way that whenever you are supplying some gas liquid or liquid system for extraction, you will see for formation of the droplet, if you are rotating that impeller at high speed, you will see that due to that shear effect the formation of the fine droplets will be there, and hence that formation of the more interfacial area, and you can get the more mass transfer. That means the extraction process will be there, more extraction phenomena you can get. So, more intense fluid dynamics where you can get it by that mixing, by making some giving some provisions of mechanical devices to produce that more fluid particles like gas and liquid droplets inside the reactor to get the better mass transfer and heat transfer. Allow reactions to proceed at the inherent rates. Also sometimes you will see if you are developing the systems or reducing the scale of the system in such a way that when that getting the contact of that gas liquid system in the suppose micro channel systems, there gas and liquid flows are there. So, you can get the more contact, more thin films between that gas and liquid, where you can get that more that reactions at the interface, and you can get the more reactive mass transfer which is happening in the particular chemical engineering process. So, this can be produced just by their inherent that properties to get the more reactive system or mass transfer system by reducing that scale of the unit. Also, sometimes more rapid mixing environment also can be suggested for the process intensification. Like in that case, if you are producing the rapid mixing environment, that can be afforded by the low reaction volumes that should enable conservation as well as that conversion and selectivity to the maximized process unit. And also residence time distribution may be substituted for the hour scale processing times that will be associated with the large conventional batch operations, which will be beneficial and also consequences for the energy consumption and process safety. So, residence time distribution and the mixing environment are the two important design parameters for the designer to actually have the uniform mixing system, to get the better mass transfer, to get the better way of reaction kinetics, and also enabling the conversion and selectivity, and also there will be some mode of application where that this scale reduction may be helpful based on these mixing characteristics. Now, main problem is that why to learn about this mixing phenomena. Basically, that understanding of the mixing is desired for the purpose of optimized operation and the design of industrial scale reactors. And also in many cases you will see that there should be a simultaneously competitive several reactions that occur, and in that case you will see simultaneously the time scale of the mixing process as well as that that degree of mixing are very important factors to give you the competitive reactions phenomena and optimized system to develop that particular reaction system. And the progress of the reactions, the product distribution and yield are governed by the mixing of the components in the mixer is the very important aspects where that your knowledge of mixing is important. So, how these reactions are being progressed and how product are being distributed and yield are governed by the mixing of the components in the mixer, that is required to know based on this mixing phenomena. Also, you can control that degree of reactions, extent of reactions or extent of mass transfer or heat transfer by controlling the rate of mixing. In that case, it is possible to intensify the process to get the better yield. Generally, mixing time is one of the most important hydrodynamic parameters in different types of chemical engineering reactors for their design and the scale up of the unit and also process. And also to intensify the yield of the commercial various chemical and bioprocesses, it is important to calculate or estimate the changes to design and operation of the process unit that lead to a reduction in mixing time. So, you have to design the operating unit in such way that your yield of the reactions should be optimized based on this reduction in mixing time. And also mixing is a particularly important process in reactor design, especially in continuous flow reactors, and designing the mixing process to yield a much shorter mixing time in comparison to the mean residence time of the reactants in the reaction vessel, and in that case it is a paramount importance for the good operation of the reactor. So, we have to know the mixing phenomena for the design of the reactor where this reaction kinetics, reactive mass transfer and heat transfer can be optimized. Now, what are the factors? Those are actually affecting the mixing time. Generally, there are several variables that affect on that mixing time or degree of mixing there. Generally we can categorize these variables in 4 types, like that first one is like dynamic variables. In that case flow rate is called the dynamic variables. So if you are increasing the flow rate, you can get the more mixing, and in that case there may be back mixing will be there may be internal circulation of the fluid mixing, so that you can get the more residence time of the fluid particles. So dynamic variables like flow rate is one of the important factor. Then you can say geometric variables like that if you are using any reactor, what is the size of the reactor, and if you are using some catalyst particles for a particular reaction, in that case what should be the the size of the catalyst particles. If you reduce the size of the particles, you can get more interfacial area of the particles, and then you can get more that mass transfer. Sometimes some adsorption processes, if you are getting more that porous materials and finer porous materials, then you can get more mass transfer because of the more interfacial area of the solid particles. So in that case, the size of the particles and also size of the reactor, if you are making that reactor size is wider, then you can get more that internal circulation of the fluid particles, that is radial distribution of that reactants will be more. So in that case sometimes it may hinder the reaction performance, but some physical processes it may be actually suitable like heat transfer processes for uniform distribution of the heat. You can suggest that more radial mixing, more internal circulation of the fluid system inside the reactor, that may enhance the heat transfer operation. So the geometric variables, you can say the reactor size, reactor length also is important, and catalyst size. Sometimes you will see in a particular reactor, sometimes gas distributors are or liquid distributors are being used for that supplying that gas as a dispersed phase of bubbles, or distributing the liquid as a dispersed phase of droplet. In that case, the distributor hole size, distributor that pore size should be optimized in such way that you can make more finer droplet or more finer bubbles just by making that hole size or orifice size of the that distributor. So that is why the distributor hole size is also one of the important factor for this mixing time or mixing processes there. Another important variables is called fluid properties. That whatever fluids are being used for that particular processes, like liquid you are sometimes being used, sometimes the solvents are being used, sometimes only slurry systems are being used. So in that case, what will be the physical properties of those systems, like what is the density, what is the viscosity, what is the that concentration of that system. So those are actually some that factors which will affect this mixing time as well as the degree of mixing. And also the level of the fluid mixer inside the column, that is height of the mixer, that is fluid mixer inside the column, that is also one important, because there one important factor is that pressure, hydrostatic pressure will be changing, as well as that to get that axial dispersion of that system, that depends on mixer height, as well as to get the more residence time for that species, you can actually elongate the unit, or you can produce that level of the fluid mixer high inside the column. Generally for fluidization system, fluidized bed system, pneumatic fluidized bed system, they are that level of the fluid mixer should be high to get that segregation of that dense region and the freeboard region there. So that is why fluid mixer height is one of the important phenomena. Now this determines the overall rate of the reactions, if the mixing times and the degree of mixing, if you know based on these factors, and much larger than the reaction times, their overall rate of reactions will be there based on these factors of those are affecting the mixing time as well as degree of mixing. Now, let us consider some phenomena for the slow reactions and the fast reaction. For very slow chemical reaction, that is relative to the time scale for mixing of the reactants, the extent of reaction is determined by the reaction kinetics and the stoichiometric proportions of the reactants there. And when the reaction is relatively fast, in that case mixing rate, physical factors like spurging design, column diameter, rate of stirring, solvent viscosity, that is those are different dynamic, that geometric, physical property variables, and also some other variables is there. Sometimes very thermodynamic variables also important there, pressure and temperature. So those factors will be actually considered for these fast reactions there to optimize this reaction. And the intense mass transfer and micro mixing capability of the rotating packed bed provides the environment to reduce the reaction time, that is 4 to 10-fold compared to the star tank reactors. That is why you will see that why this for the process intensification, this that micro mixing or micro reactors are being actually developed, because it gives this higher mass transfer. And also sometimes you see if we develop some rotating packed bed as a process intensification unit, then how this rotating packed bed provides the good environment of reacting system, where that you can reduce the reaction time 4 to the 10-fold, that is compared to the star tank reactors. So that is why nowadays star tank reactors are now actually less important than these rotating packed bed reactors. Of course, every reactors have some pros and cons, but sometimes some star tank reactors will be more easier to operate, whereas rotating packed bed may not be easier to operate, and also the investment cost will be higher compared to that star tank reactors will be there. Now you have to remember that in order to exert full control over the progress of a chemical reaction or physical transformation, the fluid dynamic environment must be sufficiently intense so that the mixing and the heat transfer rates are faster, that will be compared to the that other systems than the intrinsic chemical kinetics. So in that case you have to remember this, that control over that reacting system based on the mixing phenomena. Example, rate of polymerization that happens via a series of that radical reactions, and in that case that can be controlled by the micro mixing environment within the polymer melt. So this is one of the important examples where that you can control this polymerization reaction based on this micro mixing environment. Now the influence of mixing and the reaction rates on the reactor behavior, how the slow mixing actually progress of reaction that represented here at this simple diagram, like there is a reaction A plus B which will give you the C with the reactants like A and B that will travel in a plug flow along a tubular reactor. Whereas you can say that in this slow mixing there will be a certain diffusion, that interdiffusion will happen between this A and B, and which should be very slow compared to the reaction rate. Then C is produced near the original plane of the A and B, that is AB separation there. So for the slow reactions, it is the mechanism that progress of reaction that will be represented by this A plus B to C reactions, where that reactants A and B should be travelled in a plug flow or tubular reactor. So in that case micro channel based reactor for this process intensification are important. In this case interdiffusion of this A B should be very slow compared to the reaction rate that is happens in the other unit. And if the mixing is slow, large and varying concentration gradients of the reactant species will exist in the different parts of the reactor. So that is also to be remembered, that how you are optimizing the system based on this mixing, whether it is slow or fast. So, if results is wide variations in the product concentrations and properties that may be deemed off spec in many applications. So, that is, you have to remember the mixing is whether slow or fast. According to that, you have to intensify the process and also develop the process unit. And slow mixing, that represents a total loss of control on the two counts. Like, one is that suppose there is a AB reactions, that AB stoichiometric ratio that will vary widely across the reactor diameter. Therefore, the selectivity for the desired product C is likely to be compromised, because more realistic reaction scheme that will usually include many side reactions there. And another point is that the most of the reaction that is give you that C in the immediate neighborhood of the plane of this A and B separation, as shown here in the figure. In this case, hence only a small fraction of the available reactor volume will be utilized, and an opportunity for the intensification will be lost. So, these are the two counts to be remembered for the slow mixing for the total loss of control. For the fast mixing, you will see when the mixing will be so fast, the AB ratio should be uniform and it should be control over the product spectrum, and also the reactor space should be used to maximize this effect, and also intrinsic kinetics are should to be allowed in a free rein, where the reactor is able to operate the maximum intensity that will be permitted by the specific chemical system. Now, if we go to that the different other mixing mechanism, like the turbulent mixing scales mechanism and mixing times. In a single phase turbulent flow systems, you will see that there are three distinct mixing scales that influence a chemical process, like macro mixing, meso mixing and micro mixing. These are the three different mixing scales generally are considered for the intensification of the chemical processes. These are defined on the basis of their characteristics length and directly related with the turbulent energy dissipation rate. So, based on the energy dissipation, in case of turbulent condition, you can actually optimize that mixing characteristics. So, that is why sometimes in a reactor some provisions are made to get the intense mixing inside the fluid based on this turbulent flow. If you are supplying the fluid mixer or inlet streams as a high flow rate, and if you are using some provisions like baffles inside the reactor and cross baffles, or sometimes you see some nowadays that helical coil systems are also important there, and inside that helical coils, if you use some some nozzles that will struck your flow of the system. So, at high flow rate, whenever it will go through these provisions of these helical systems or some baffle systems, there there will be a intense shear stress inside the reactor. So, based on that intense shear stress, high energy dissipation inside the reactor, this fluid gets more turbulent, and because of which there will be a higher energy distribution and dissipation and get the more mixing inside the reactors. And the path of the fluid mixing, you may also get the change by just giving these provisions of these baffles or that some nozzles or some obstructions inside the reactors, so that the mixing times maybe will be higher or lower based on that design. Now, if we see this figure as shown here in the slides, that turbulent mixing, how actually this in various length scales these mixings are happened. Macro mixing, meso mixing and micro mixings are there. So, if we are considering the modes of this mixing, then we can have this macro mixing like in the vessel, that is bulk convection of this fluid will be happened, whereas in the meso mixing, in that case turbulence eddies will be formed, some chunk of the fluid elements will be that generated inside the reactor or inside the unit, and those chunks of the fluid elements will be called as eddies, which will be arbitrary, or that random motions will be there, and getting that intense mixing inside the reactor or unit, and there will be formations of that vortex shading by these eddies and by energy dissipation. So you can get this meso mixing. This type of phenomenon is called meso mixing. And here this micro mixing, in this case you will see that producing some channel based, where that plug flow phenomena will be produced, and some engulfment phenomena will be produced of this fluid element, or deformation of this fluid element, just making that different provisions here in the reactor, inside the reactors, or sometimes that coil type reactors will be produced, so that there will be a change of engulfment, like maybe that secondary flow will be produced, that will give you the more mixing of the fluid element. And that deformations also, sometimes some provisions will be there that fluid elements will be deformed, fluid streams will be deformed, and in that case there will be a mixing. And also diffusions will happen there, that is molecular diffusions will happen, molecular level. The convective diffusions will be less compared to that molecular diffusion there through the thin fluid layer, so that you can get the more that molecular level diffusion mechanism. In the case of macro mixing, you will see that for this macro mixing, turbulent diffusion there should be there, so inertia, convective inertia will be there, and also turbulent diffusion in case of meso mixing will be observed, inertia, convective terms will be there, that is convective inertia will be produced, because of which there energy dissipation. And in the case of micro mixing, there will be a momentum diffusion and molecular diffusion, both will be there, because there engulfment formation and deformation of that fluid element. That is why momentum diffusion and molecular diffusion will be the major effect there. And if you are considering the time scale, what will be the time that will be required for the macro mixing? For that macro mixing, you will see that whatever the energy will be dissipated, that will be directly related. In that case, degree of mixing will be directly related to that energy dissipation, whereas mixing time will be inversely related to that energy dissipation. If you are considering the epsilon as energy dissipation, so for the macro mixing, the time of mixing will be proportional to the epsilon to the power minus 1 by 3, whereas for turbulent eddies it will be also the same, that should be proportional to the inverse of this 1 cubic root of that energy dissipation, that is TMIT here. Similarly, for micro mixing, this time of mixing or mixing time, it is inversely proportional to the square root of that energy dissipation. So this based on this time scale, that macro mixing, meso mixing and micro mixing, how this time scale is actually depending on that energy dissipation, that you can get it from this idea. Now, energy dissipated mixing, the intensity of the mixing at each of these scales, that is macro, meso or micro, is significantly influenced by the that mechanical energy input into the system by mixing device, and it is generally assumed that higher energy input translates into a higher energy dissipation rate for better mixing. The kinetic energy imparted to the fluid is ultimately dissipated as internal energy, which occurs at the smallest length scales of turbulence, and that will give you that the time scale, which will be represented by that Kolmogorov that time scale there. Now, characterization of the various mixers and reactors in terms of their energy dissipation rates. Here some examples. Some intensification of the unit are there, like start tank reactors. In that case, energy dissipation rate per unit mass of that fluid system, that will be 0.12 100 watt. And for the static mixture, for this mixing, their energy dissipation is 1 to 1000 watt per kg. Impinging jet reactors are important reactors, where that fluid is actually coming into the pool of the liquid and impinges on the pool of the liquid to make the or entrant the other fluid element. So, this is called impinging jet reactors. They are intense mixing by the jet energy. So in that energy dissipation rate should be 20 to 6800 watt per kg. Like rotor stator spinning disk reactor, thin film spinning disk reactors, their energy dissipation should be or is are less than 6000 watt per kg. So this illustrates the potential capability of the intensified systems such as static mixer, rotor stator mixers and the spinning disk reactor among others to provide the higher level of mixing intensity than the other conventional mixing devices. In the case of macro mixing, that involves the mixing on the macroscopic scale, which refers to the scale of the vessel or reactors. The process is often referred to as the distributive mixing, and it is achieved by bulk motion of the fluid element, and that is transported by that liquid at the macroscopic scale, and resulting in uniform spatial distribution of the fluid elements across the reactor volume. And in a continuous flow reactor, you will see that the macro mixing process directly influences the residence time distribution of the feed stream that is introduced into the reactor. And the macro mixing time in a mechanically stirred baffled tank, that is tau mac, we can represent it, that will be a function of the mean circulation time, that is means how much circulations time will be there inside the reactor of the fluid element, that will affect this macro mixing time. So that circulation time is actually defined as volume of the reactor divided by what is the flow rate of the circulation, or you can the circulation rate. And in a vessel that is configured for the optimized mixing, the tau max should be 3 times of that circulation time. In case of star tank reactor, that circulation time is defined by this equation here, the V by CD into N D cube. CD is the discharge coefficient of the impeller if it is being used for the star tank reactor, and it is a constant which typically varies between 0.7 and 1, that depending on the impeller design. In a non-optimized systems, this macro mixing time should be 5 times of that circulation time, and the mean circulation time is generally expressed in terms of the impeller pumping capacity also, that is denoted by QC here. For meso mixing, that will refer to coarse scale and dispersive mixing via turbulent eddies, that eddies will actually arbitrarily randomly moved inside the reactor, and it will be characterized by 2 different mechanisms. Like one is turbulent dispersion of the fresh feed that will be introduced to a vessel which mixes with its total surroundings, and other is inertia convective breakup of the large eddies. Sometimes you are using that different provisions that eddies should be broken up into a smaller eddies, and then you can get the very small scale of this interaction of these 2 eddies there, and then you can enhance that meso mixing time there. The characteristics time scale associated with the turbulent dispersion, by turbulent, that will be dispersion, the turbulent dispersion, it is denoted by that time scale of that the meso mixing dispersion. So that will be represented by tau d, and it can be defined by that QF by UD turbulent. Here if R pipe is less than equal to LD, LD is the that dispersion length, characteristics length scale of the dispersion, and also R is the pipe diameter. That D turbulence, the dispersion coefficient of that turbulent medium and the turbulent scheme of this dispersion. So tau D, that will be R square pipe by D turbulent if pipe of the reactor, or that radius of the pipe if it is almost equals to the characteristics length, or if it is greater than characteristics length, you can define by this equation here. And also you can say that dispersion coefficient at this turbulent motion, it will be 0.12 epsilon to the power 1 by 3 into LD to the power 4 by 3. This epsilon is called energy dissipation per unit mass, and LD is the characteristics length in that turbulent dispersion. And the inertial convective meso mixing time scale, that will be represented by tau s, that will be defined by this equation here as shown in this the slides, where A is a constant that will have a value between 1 and 2 that depends on the turbulence level in the system. And then the micro mixing represents the final stage of the turbulent mixing process, which proceeds at mass final length scales that macro or meso mixing that will referred by Kolmogorov or Wessler's length scale. The Kolmogorov the length scale represents the smallest scale of the turbulence before viscosity effects that will dominate, and also Wessler length scale, it is denoted by eta B, represents the smallest scale of the fluctuations prior to the molecular diffusion. So, micro mixing molecular diffusion prevails there. Also this Kolmogorov or that that Wessler length scale can be defined by this here equation given here eta k and eta b, where this Schmidt number Sc for liquids is typically for the order of 10 to the power 3. So, that eta b should be very less than eta k. For aqueous solutions in turbulent regimes, this eta k is of the order of 10 to 30 millimeters. So, based on this, that criteria of this length scale of this micro mixing, that devices are developed for getting more mass transfer and heat transfer in the systems. I think I have covered some this process intensification phenomena based on this mixing characteristics. This lecture will be helpful for the process intensification criteria where you are considering the design of any micro reactors or other reactors based on this time scale, and it will be helpful for you for this process intensification system. And for further reading, I am suggesting the textbook to follow, and in the next lecture onward we will also discuss something more about this, that the process intensification based on other characteristics. So, thank you for this lecture.